Hello, Advanced Algebra 2. Welcome to the Concept 31 Part B notes. In these notes, we're going to find the sums of infinite geometric series. Some of them, we can't find all the sums of infinite geometric series, but some we can. All right, so let's talk about partial sums of an infinite geometric series. So the sum S sub n is the first n terms of an infinite series called a partial sum. So this capital S stands for sum. The partial sums of an infinite geometric series may approach what we call a limiting value. And then that limiting value, we will call that the sum. So look at this example. We're going to find a partial sum. So consider this infinite geometric series. 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32. It's geometric because each time each of the elements or in the series, you multiply by a half to get the next one. So the sum of the first term is just a half. The sum of the first and the second, so capital S sub 2, that means the partial sum of just the first two terms. So a half plus a fourth, if we get a common denominator, that gives us 3/4. Our next partial sum is when we add up the first three terms. So a half plus a fourth plus an 8. Getting a common denominator of 8, that will give us 7/8. So watch this sum closely and see what happens to it. So now the sum of the first four terms, which is a half plus a fourth plus an 8th plus 1/16, if we get a common denominator of 16, that will give us 15/16. See how our sum is getting closer and closer to 1. So now the sum of the first five terms, using a common denominator of 32, you can probably guess, will give us 31/32. And so that pattern will continue and continue, breaking it down into smaller and smaller bits and getting closer and closer to 1. So we say that S sub n approaches 1. And so since it's approaching 1, the sum of this infinite geometric series is 1. Now take a look at the graph. So we have the n term on our x-axis and then S sub n on our y-axis. And so we're going to plot the sum of the first term, which is just a half, and the second term, which is 3/4. I'm going to change those into decimals because decimals are a little easier for me to graph. So there are the decimal equivalents to 7/8, 15/16, and 31/32. So you can see that this looks like, an exponential curve, and that it's getting closer and closer to our 1 value. So we say that the sum of this infinite geometric series is 1. Now here's a formula that you can use to find the sum of some infinite geometric series. So S, which stands for sum, equals a sub 1, which is the first term in the series, divided by 1 minus r. And remember, r is the multiplier. Now this works if the absolute value of r is less than 1. If the absolute value of r is greater than 1, that means that each time your multiplier is bigger than 1, then the series has no sum. So let's find the sum of these series. On A, we have an infinite series going from 1 to infinity. Notice it's geometric, and notice that our rate is the 0.7. So yes, this has a sum because our rate is less than 1. So plugging our values into the formula, our first term, and we can tell just by looking at the rule by our sigma there, our first term is 3 over 1 minus the rate, so 1 minus 7/10. So that would simplify to 10. Now on this next one, we can find the rate, and notice from one term to the next, I have a typo there, that should be 27. We have a multiplier of 3. This geometric series will not have a sum because the rate is increasing and increasing and increasing. So it's greater than 1. So we'll never be able to capture that sum. It'll just keep getting bigger and bigger. Now with C, look at and let's figure out the multiplier. 1 to 3/4, to negative 3/4, we can get that by multiplying by negative 3/4, and then the 9/16 multiplying by another negative 3/4, and then another negative 3/4. So this series does have a sum because the absolute value of our rate is less than 1. So the first term is 1 over 1 minus a negative 3/4, and then simplified, that is 4/7. So in D, we have that infinite series going from 1 to infinity. So our rate is negative 1/2. The absolute value of that is less than 1. So we do have a sum. So using the formula, now we don't see the first term, but I've written it in there. It's an understood 1. So 1 over 1 minus r, and that would give us 2/3. Now on E, notice our r value of 5/4. That is greater than 1. So that means that the sum of this series will keep increasing. It will not approach a value. So we do not have a sum. Now this last one, we have 3/4, 3/16. So we can get from one term to the next by multiplying each time by 1/4. So our r value is 1/4, and that is less than 1. So this series does have a sum. Our first term is 3 over 1 minus r, 1 minus 1/4, so it would be 3 divided by 3/4, which would be 4. Look at this real-life problem. So a pendulum that's released to swing freely travels 18 inches on the first swing. On each successive swing, the pendulum travels 80% of the distance of the previous swing. What's the total distance that the pendulum swings? So we've got just our first term in this situation is 18. And then what's happening is that it is decreasing by 20%, or it's being multiplied. Each subsequent swing is 80% of the first. So as a rule, it would be 18 times 0.8 and then raised to the n minus 1. So since our r value is less than 1, we will have a sum. So our first term is 18, 1 minus our r value for our denominator, and then that would be 90 inches. All right, that concludes our notes for Concept 31, Part B, how to find the sum of an infinite geometric series.